Good day, everyone, and thank you for joining me today. My name is John Costa, and I am excited to present my project, Predicting Hazardous Near-Earth Objects. This presentation showcases how predictive analytics can help address one of humanity's most critical challenges, planetary defense. Let's begin by defining the scope. Near-Earth objects, or NEOs, are asteroids or comets that come close to Earth's orbit. While many of these objects are harmless, some pose catastrophic risks. The asteroid that caused the Tunguska event in 1908, for instance, was only about 50 meters wide, which flattened over 2,000 square kilometers of Siberian forest. As our knowledge of space grows, so too does the number of NEOs we identify. NASA alone tracks thousands of these objects. The challenges lie the challenge lies in determining which one requires immediate attention. My goal in this project was to develop a machine learning model to classify hazardous NEOs with high accuracy and recall, enabling better prioritization of resources. Today, I will walk you through the process I followed using the 7-step business analytics process. This approach provided a structured framework for the project, guiding every decision from problem definition to deployment. Let's begin. To understand the importance of this project, let's first dive deeper into the problem. Near-Earth objects vary widely in their size, velocity, and trajectories. While most pass harmlessly by Earth, a small subset could collide with our planet and cause significant damage. To illustrate the scale of the potential damage, consider the Chicxulub asteroid, which scientists believe led to the extinction of the dinosaurs. While that was an exceptionally large asteroid, even smaller objects, if they hit urban areas, could result in devastating loss of life and infrastructure. The key challenge lies in resource allocation. Agencies like NASA track thousands of NEOs, but monitoring all of them with equal intensity isn't feasible. Prioritization is critical. By accurately classifying hazardous objects, we can ensure that resources are focused on those that pose the greatest risk. The primary research question for this project was, can we develop a predictive model that classifies NEOs as hazardous or non-hazardous with high accuracy and recall? Addressing this question is not just about technology, it's about saving lives and safeguarding our planet. The foundation of any predictive model lies in its data. For this project, I used a dataset sourced from NASA's open APIs in Kaggle. This dataset contains over 90,000 records, each representing a unique NEO. It includes 10 attributes such as size, velocity, proximity to Earth. The target variable hazardous is a binary label indicating whether an object is considered hazardous based on specific criteria. These criteria are established by NASA and include factors like the object's distance from Earth and its estimated impact energy. The data set is well structured and provides a comprehensive overview of NEO characteristics. However, it is also presented some challenges. For example, some features lacked variability, which meant that they provided no meaningful information to the model. Addressing these challenges was a critical part of the data preparation, which I'll discuss next. Data preparation is one of the most time-consuming but essential steps in building a predictive model. For this project, I focused on cleaning the data set and selecting the most relevant features. First, I removed the constant features such as orbiting body and sentry object. These variables provided no variability. Orbiting body was always Earth, and sentry object was always false. Including them would have only added noise to the model. Next, I conducted a correlation analysis to identify relationships between variables. One notable finding was the perfect correlation between estimated diameter min and estimated diameter max. This makes sense because they represent the same characteristic in asteroids' size. To simplify the dataset, I retained estimated diameter min and excluded estimated diameter max. After these steps, I selected 4 features for the model. Absolute magnitude, this measures intrinsic brightness and inversely correlates with size. Relative velocity, the object speed relative to Earth, which is critical for understanding potential impact energy. Miss distance, how close the object comes to Earth, a direct measure of risk. And finally, estimated diameter min, the minimum estimated size, which provides a lower bound for potential impact size. These features were chosen not just for their relevance, but also for their independence from each other, ensuring the model would perform effectively without redundancy. Once the data was prepared, I moved on to the modeling phase. I tested several machine learning algorithms, including decision trees and random forests. Each algorithm has unique strengths, but random forest ultimately emerged as the top performer. Random forest is an ensemble learning method that builds multiple decision trees and aggregates their outputs. This approach reduces overfitting and improves the model's generalization ability. To optimize the random forest, I made several refinements. Increased the number of trees from 100 to 300. More trees improve the model's robustness and accuracy. Expanded the maximum tree depth from 50 to 100, allowing the model to capture more complex patterns in the data. Also applied pruning with a confidence level of 0.10 to prevent overfitting. Used random splits to ensure the model explored different combinations of features during training. These refinements significantly boosted the model's performance, as we'll see in the evaluation phase. The evaluation phase revealed just how effective the random forest model was. Key performance metrics included accuracy, 91.59%, AUC, area under the curve, 0.941, recall, 40.50, precision, 67.29. Let's unpack these results. An accuracy of 91.59 indicates that the model correctly classified the vast majority of NEOs. The AUC of 0.941 is particularly impressive as it demonstrates the model's ability to distinguish between hazardous and non-hazardous objects. Recall at 40.50% ensures that a significant portion of hazardous NEOs are identified. While this might seem low compared to accuracy, it's a critical metric for planetary defense. Missing even one hazardous NEO could have catastrophic consequences. Precision at 67.29% indicates that most of the objects classified as hazardous truly are hazardous, minimizing false alarms. The confusion matrix further illustrates this balance, showing how the model performs across different scenarios. Together, these metrics highlight the random forest model's strength as a tool for planetary defense. To better understand the model's effectiveness, I analyzed the lift chart. This chart provides a visual representation of the model's ability to rank observations by risk. The lift chart shows that the top bins contain a disproportionately high number of true positives compared to random selection. For example, the first bin contains the highest concentration of hazardous NEOs, demonstrating the model's ability to prioritize high-risk objects. This prioritization is invaluable for decision-making. By focusing resources on the top bins, organizations can ensure that the most dangerous NEOs are studied and monitored first. This insight adds significant value to the model beyond just its classification accuracy. The final step in this project is deployment. The plan involves integrating the random forest model with NASA's tracking systems via APIs. This enables real-time data input and prediction, ensuring that new NEOs can be classified as soon as they are discovered. The model will be hosted on a cloud-based infrastructure, allowing it to scale as the volume of data grows. A user-friendly interface will provide visualizations of predictions, making the results accessible to both scientists and decision makers. Regular retraining of the model will ensure its predictions remain accurate as new data becomes available. This iterative approach ensures the model remains as a reliable tool for planetary defense. In conclusion, this project demonstrates the power of predictive analytics in addressing a critical global challenge. By following the 7-step business analytics process, I developed a random forest model that combines strong performance metrics with actionable insights. The model not only classifies hazardous NEOs, but also ranks them effectively, providing a robust foundation for prioritizing resources. While the results are promising, there's always room for improvement. Future work will focus on refining recall and exploring additional features such as trajectory anomalies. This project underscores the transformative potential of data-driven decision-making in planetary defense. Thank you for your time, and have a good day.